Good morning, everyone. Thanks for attending to this session. I would like to present my work done in collaboration with Adrián Corrochano, Javier Sierra, David Fabre, and Soledad Leclench about modeling double concentric jets with linear and nonlinear approaches. Let's start with the motivation to study this type of flows. Why are they important? Well, they can be found in several industrial applications as an effective way of mixing fluid streams. For example, industrial burners, air blast atomizers, and jet pumps. All of them present this concentric jets configuration, a center jet surrounded by an annular jet. These flows can be found as well as a way of reducing noise in technological application. We are modeling this flow as we can see in this slide. We have two jets with inlet velocity entering an axisymmetric computational domain. This would be a wall, while here we impose outflow boundary conditions. This configuration has been validated with the results of Canton and co-workers, and the cases here studied are one case with the same velocity for the two jets, for the inlet, from the inner and the external velocity. A second case where the inner velocity is twice the outer velocity. And a third case with the opposite. The outer velocity is twice the inner velocity. All of them are 1 unit of distance apart, and the Reynolds number tested is in a range between 1 and 2000. Let's remind that the Reynolds number is a non-dimensional parameter that compares the convective terms with the viscous terms. Numerical simulations have been performed with the open source code StatFem, an interface to the finite element solver FreeFem. It has the advantages of mesh generation and adaptation, and a web publishing system optimized for team working. With this code, we run a linear stability analysis over the Navier-Stokes equation. A small perturbation is imposed and introduced to the equations. If the perturbation is decomposed in space and time, an eigenvalue problem is generated, which provides the eigenmode of the perturbation with its growth rate and frequency. More numerical simulations have been carried out employing the open source code NEC 5000, using a spectral spatial discretization. With this code, we have solved the nonlinear Navier-Stokes equation, different than the previous case with that was a linear analysis. It has the drawback of the high computational cost needed to run the simulation, but with high accuracy. We intend to identify linear modes, steady and unsteady modes, to continue the nonlinear analysis of the located modes. To analyze this, we employ dynamic mode decomposition, a technique that provides this type of expansions, with a nonlinear mode with its growth rate and frequency. The modes here obtained will contain the linear ones, and in addition, DMD can study the complex dynamics and mode interactions. With this expansion, we can extrapolate the data and forecast a model changing this temporal term and reducing the computational cost of the numerical simulations. Let's see the results. We present here the base flow. The two concentric jets, here we can see the stringwise velocity. The jets eventually get together, and here we can see a region with a recirculation bubble. We proceed with the linear stability analysis of the three cases, and we identify the steady and the unsteady modes for these three cases studied. Here we can see the shape of the modes for a Reynolds number 2000. They are quite similar, and the activity is focused in this region, in the region of the recirculation bubble. This means that the changes in the flow will be from the perturbation and oscillations inside the bubble. Once that the modes are identified, we observe the increase of the growth rate. If we took as the case 1,1 as reference, we can see the increase of the growth rate uniform in the steady case, but it's non-uniform if we look at the unsteady case. Finally, we have studied the critical Reynolds number. It identifies the point where the character of the solution changes from unstable to stable. Again, we set as reference the case 1,1, and we see that if we increase the outer velocity of the critical Reynolds number decreases in both cases, a result that is expected. But on the other hand, if we increase the inner jet velocity, the critical Reynolds number increases as well. In the steady case, it remains very similar in the unsteady case. This effect suggests a control strategy to delay the flow instabilities. Finally, we studied the data obtained from the DMD analysis. It identified similar modes that the one obtained by the linear analysis, and in addition, identified 20 modes when the data is collected in this temporal range, and 12 modes when the data is collected in this temporal range of the numerical simulations. Next, we adapt the temporal term to predict the solution in this time interval. Here, we compare the exact solution, the black line provided by the NEC 5000 simulation, and the predicted one, the red line, that would be the solution by DMD model. The computational cost, as we can see, is reduced with these corresponding errors in both cases. So to conclude, we have analyzed 3 different cases of double concentric jets, identifying their steady and unsteady modes by linear stability analysis. The critical Reynolds number has been obtained as well, suggesting strategies for flow control. And finally, using DMD expansions, the solution can be predicted decreasing the computational cost of the simulation, employing a model based on physical modes for soft computing. It is worth to mention that in a first intent, we try to create a physical-based model only using the modes identified by the linear analysis. However, when using the DMD-based model, we found that the predictor of the flow with high accuracy, we also needed to take into account the nonlinear mode interaction. So, thank you very much.